Today we are going to talk about exponential functions. In the first part, I'll explain each term of the equation and the shape of the graph. This is the equation of an exponential function, where the variable x is an exponent. In this equation, a is the initial amount, which is always larger than 0. B is the rate of change that has to be a positive number but not equals to 1, as there will be no solutions of y when x is not an integer if b is a negative number. Also, b is not equals to 1 as we want an exponential graph instead of a horizontal line. Now x is the number of time interval. From the exponential function, we substitute a equals to 1 and b equals to 2 with different x value. First, we substitute x equals to negative 4 and we get 0.0625, then 0.125 for negative 3, and so on. When we substitute a equals to 1 and b equals to 0.5 with negative 4, it gets 16, then 8 for negative 3, and so on, to get these two exponential graphs. From this graph and these sets of data, you can conclude that if the value of b is larger than 1, the y value are increasing, as in like this graph, which is an exponential growth graph. When the b value is between 0 and 1, the y value is decreasing as x value increase, which show in this graph. And this is an exponential decay graph. After explaining the terms of exponential function and the shape of graph, Lorraine will further point out some applications of exponential function in science, clinical, and business aspects.
My name is Lorraine and I'll be presenting the applications for the exponential function. First, we have radioactive decay, which can be used to estimate how much of a radioactive isotope is left after a certain time. And this is a very important application which has been used in various fields of chemistry. Secondly, we have carbon dating, mostly used by geologists, where the carbon-14 is used to determine the age of fossils and rocks. And this has played a huge role in explaining the processes such as evolution, where they dig up the fossils and then they can tell how long they've been on the earth. We also have nuclear imaging, where radiation means patients can be diagnosed through non-invasive procedures. And we also have radioactive drugs and tracers, which are used to analyze the human anatomy. Also, we have financial businesses such as banks, which use exponential growth to calculate compound interest, and also population growth, where we estimate the size in years to come of a population given that there are no restrictions in resource and space.
Hi, my name is Moira and I'm going to take you through the examples of exponential growth and exponential decay. So part A, determine an equation for fruit bat's population P as a function of the number of years T since the end of 2005. So the equation for exponential growth we have is y is equals to A, parentheses, 1 plus r, parentheses close, and raised to power t. where A is the initial amount, R is the rate, and T is the time. So 6800 is going to be A, and the rate is 3.5. You have to convert it to decimals, so it's going to be 0.035. So it's going to be plus 1, 0.035 in the parentheses, raised to power T. So we'll just do some mathematics in the parentheses. So it's going to be 6800, 1.035 in the parentheses, and raised to power T. Moving on to the part B. So part B is sketch a graph of fruit bats population as a function of time on the axis below for the 50 years following 2005. Be sure to label your y-intercept and your graphing window. Mark fruit bats population at the end of 2055. So till 2055 it's going to be 50 years. So we'll just work out it through the equation y is equals to a 1 plus rt. So time is over here is 50. So it comes, we just put everything in the equation and solve it, and it's come out to be 38,000 residents. We'll take population on the y-axis and time on the x-axis, and we can plot the graph. Like at 50 we can plot 38,000, and on 0 we can plot 6800, which is the initial one, and we'll get the curve as it's shown in the figure. And it shows that it has exponentially increased over the 50 years. So moving on to part C, which is use your model from part A to predict the number of residents at the end of 2010. So we use the same formula. So T is 5 years over here, and A is 6,800 people. So we'll just put everything in the formula, and it's going to be 8,076 residents. And it's pretty much the same. Just put the values in the formula, and you'll get the answer and do some mathematics. And now we'll move on to exponential decay. The formula for exponential decay is y is equals to a 1 minus r raised to power t. The only difference between the two formulas is 1 minus r and 1 plus r. So for the decay we use 1 minus r, and for growth we use 1 plus r. So the question is, hydrologists have found that the amount of water that a soil can absorb in inches per hour decreases by 20% for each hour that the soil is flooded with water. A particular dry soil is initially able to absorb 4 inches of water per hour. So part A, write an equation for the amount of water A, T, in inches per hour that this soil can absorb if T represents the number of hours since the soil was flooded. So we use the equation y is equals to a 1 minus r raised to power t. So it's 20%. We'll just convert it to decimals, which is 0.20. We'll do some mathematics. So it's going to be 0.8 in the parentheses raised to power t. 4 is the initial amount we have over here, and pretty much everything is the same. So moving on to part B. It's sketch a graph of the function that you wrote in part A on the axis below for all times on the interval 0 to 10. Label your y-intercept. So I have done the working on the side for the time from 1, 2, 4, 6, 8, 10. I have just simply put everything into the formula and worked out the values. So I have shown how I've done the for t is equals to 10. So initial amount is 4 and 0.8 in the parentheses, and t is 10. So if you just do some mathematics, we'll find 0.43. I have used the same formula for the rest of the other times as well. And when we plot this into the graph, it comes out to be the curve as it's shown in the figure. So on the y-axis we have taken the absorption, and on the on the x-axis we have taken time. So pretty much just plot the values and it's going to give you the curve, and that's it. Thank you.